All right, let's take a look at our introduction to chapter 4.4, spanning sets. In this video, I'm just going to introduce you to the idea of what a spanning set is and some of the major types of questions we're going to be asked in this section. So, first definition we need to look at is what's called a linear combination. You've seen linear combinations before. A linear combination of vectors is the sum of some scalars times some vectors. That is to say, it's a macro of the two operations we have in any vector space. We have a scalar multiplication by a vector, and then we have the sum of vectors, and so this is just a large linear operation combination, hence the name linear combination. It is vector addition of scalar multiples. Okay, that's pretty straightforward. We've seen this kind of thing before. I just want to show you some examples that you should be familiar with. So here in our first little exercise here, I have written at the top general versus particular. And what these are general versus very particular forms of linear combinations. Over here on the left, the collection of vectors S that I'm using is e to the x cosine x and sine x. So this is my collection of vector 1, vector 2, vector 3. And I have the sum of those vectors, c1, v1 plus c2, v2 plus c3, v3. I have a linear combination. And those are quote-unquote vectors, right? Air quotes around my fingers you can't see. Those are vectors. The v sub I are elements of, I guess the parent space would be CKI, continuous functions with at least k continuous derivatives over some interval. That's our function space for well-behaved functions. Over here on the right side, I have a linear combination of those. That's C1 e to the x plus C2 cosine x plus C3 sine x, where specifically C1 is 0, C2 is 1, and C3 is 5. So that is a very particular linear combination from the general family of linear combinations. Okay, moving down here, I have another example. This one is actual traditional vectors. This is a collection of two vectors, 1, 2, 5, negative 1, 0, 1, and here we just have constant 1 or scalar 1 times 1, 2, 5 plus scalar 2 times negative 1, 0, 1. And here our vectors v sub I, our v sub i's, v1 and v2 here, is from R3. So vector 1 and vector 2 are from R3 here. And over here we have a very specific linear combination of those two. This is 2 times the first vector plus 1 times the second vector. And here we were actually able to simplify it, right? 1, 4, 11. Up above, I can't really simplify this expression any further than that. But here I know how to do a little bit of vector addition, so I was able to simplify that. Okay, so those are just some examples that you should be familiar with in terms of operations, but now we're using new terminology, right? Linear combination of a collection of vectors. Okay, so here's the formal definition. The formal definition of what it means to be a spanning set, which is the idea that we want to talk about here. Definition: if every vector v ever in a vector space can be written as a linear combination of vectors from the set, I guess I might want to write S equals here. That's what I'm referring to above. The set S, v1, v2, dot, 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 all the way up to vk. Then we say v is spanned or generated by the v sub I. And this is just shorthand notation for the collection of all these different v's. So what does that mean? Well, it means that I'm interested in, if you take a general element or a random element from a vector space, does the set containing the vectors v1 through vk generate what is basically a collection of basic building blocks? Am I able to build anything in V from this collection? and using a linear combination of these vectors. So then we say that V is spanned by those vectors, if that's the case. And we call this set S equal to the V1, V2, dot, dot, dot through Vk, or the V sub I. We call that a spanning set. Or we say the V sub I spans V. Okay. Now, the majority of questions involving spanning sets in this chapter fall into one of three cases. The first one is V in the span of S? And what this means here is you are given a very specific vector. So suppose a specific V vector is given, and we want to know if V, this is notation here, V is an element of span S for some S, which is a collection of vectors. Right? So, and that's a true or false question. And so let me show you what I'm talking about. Suppose S, the collection of vectors, is something like 1, 0, 1, 0, and negative 2, 3, 0, and 1. It doesn't really matter what these are right now. And 1, 1, 1, 0. And V, the given vector, is something like 5, negative 2, 8, and 10. Right? It's random, well, maybe not random, but a very specific element of R4. And so the question is V an element of the span of S? That's the question. So what does that mean? Well, it means, is there a linear combination of vectors, almost write vegetables, vectors, vectors from S that equals V? So that would look like this. C1 times, let me do this in a different color. All this red is starting to get monotonous. C1 times 1, 0, 1, 0 plus C2 times negative 2, 3, 0, 1 plus a C3 times 1, 1, 1, 0 is equal to 5, negative 2, 8, and 10. So this is the linear combo of S vectors, and this is the specific vector we would like to know is in the span of those vectors. Now, this is actually just going to turn into a linear system. We're going to use either techniques of chapter 2 or chapter 3 to solve this system. So this will be a linear system with variables C1, C2, C3. So if there is at least one solution, the system will have C sub I values that make this true, and we would conclude that V is in the span of S. If there is no solution, then no such C1, C2, and C3 exist. And V is not in span S. Okay. The next question we might be asked is, does S span V? So this is a slightly different question, right? What this means is, can we generate everything possible in the vector space? So is it possible? Let me just bring this down lower here. Is it possible to generate every vector in V using a linear combination of the vectors from S? So that would look a little bit different, right? That would look like this. The linear combination would be the same. So for the same S, C times 1, 0, 1, 0 plus C2 times negative 2, 3, 0, 1 plus a C3 times 1, 1, 1, 0. Is there a possible solution of C1, C2, and C3 that will generate any vector possible in R3, or sorry, R4? This is a general vector in R4. Now we're going to look at these examples in detail in the next video. I just wanted to give you a feel for what these questions mean. So again, the same thing is true. If the system is consistent, then we would say S is a spanning set for the vector space V. So that's a little bit different, right? In the previous one, we're talking about, is it possible to just build one specific vector, and then that vector is in the span of S? But here we're talking about whether or not we can build every possible vector in V, in which case we then refer to S as a spanning set. Okay, so if the system is inconsistent, then S is not a spanning set. And I need to pause here. If I just leave this statement as is, it's actually false. It's supposed to say, if the system is inconsistent, then S is not a spanning set for V. It could span some other set. It just doesn't span V because I wasn't able to build everything in V. Okay. And then the last question that we can be asked is sort of a bit more general. What is the span of V? That means what is possible to generate from linear combinations of S. So just to sort of reiterate what these ideas mean, I want to talk about a powerful analogy that I use every time I teach this class, and that is directly related to a simple concept that I'm sure everybody's familiar with. I'm always surprised, and it's only happened one time, when I ask the following question, and the question is yes. Did anybody through their childhood grow up without playing Legos? And I think it was only one person in my entire history of teaching mathematics that answered yes, I've never played with Legos before. So when I was a kid, I inherited a bunch of Legos from my uncle. Tons of Legos. Legos coming out my ears. But they were Legos from like the 60s and the 70s, right? Just basic bricks. Not your fandangled Harry Potter Legos and prefabricated forms. I'm just talking about basic blocks here. And every time I would go to the store, like Target with my parents, we'd walk in the front door and I would excuse myself and run straight over to the toy aisle. This probably sounds familiar for a lot of people, right? And then I would fantasize about getting the largest possible Lego set that they had, right? Some $400 Death Star set. That's a new reference. Actually, when I was a kid, it was just like a castle or whatever, and it was probably $20. And my parents were like, a little steep. And so this is how the conversation went with me and my dad. This is me. Dad, I need this. And probably some of you have heard this before. My dad would reply, you don't need that set. You got so many Legos at home. I bet you if we went home and we could build that out of the Legos you have. And to which I would throw myself on the floor and just have a tantrum, right? So what are we talking about here then in terms of Legos? This first question is, we go to the store, I point to a set and I say, Dad, I need that specific set. I need the castle. I need the tower. I need whatever. I need this spaceship. And my dad says, no. You've got enough different blocks at home. If you use a certain number of the first block, plus a certain number of the second block, plus a certain number of the third block, you should be able to build this thing that I don't want to buy you. Now, me and my dad came to actually a pretty good arrangement. We would go home and he would actually try to build it with me. And if we could build it, he wouldn't buy me the set. But if we couldn't build it, he would buy me the set. Now that's actually kind of a lie. He wouldn't buy me the set. He would go get me some other cheap set that had the one missing piece that I needed to add to my collection at home. But the idea is the same. And so here it is. I want to build this specific set. We have bricks at home and I can have any number of them, any scalar multiple of them that I want. And so when I add them all together, I put them all together, the question is, can I build this? And if the system has a solution, then the answer is yes. This construction is in the span of my Lego bricks. If the answer is no, it means I'm missing at least one brick that is terribly important to this set. Okay. This next question is a little bit more general. This is not can I build something specific, but there's different categories of Legos, right? There's like space, city, Lord of the Rings, Harry Potter, castles, medieval, right? And this is a bit more like different complete universes of Legos, right? Each vector space is a different category of Legos. So maybe one vector space is Harry Potter, and another vector space is city, and another vector space is castle, right? Classic. Or Space Command or something like that, right? And so the question is, not can I build one spaceship specifically from all the spaceship vehicles or the space sets, but do I have enough bricks to build every possible Lego construction in that grouping, that space grouping? So this is a little bit more general. This is, can I build something specific like one spaceship? And this is, can I build every possible spaceship that Lego sells as a collection? And then the last question is a bit more general. What is the span of S? This is just simply, what is it possible for me to actually build? Not something specific, not a whole collection of sets. What was this? -2, 3, 0, 1, plus C3, 1, 1, 1, 0. What is it possible for me to build in general? What are my limits? What is the span of my bricks in general? Anyway, that's the Lego analogy. We're going to be revisiting that idea quite a bit in the videos to come. This has been, what is the definition of a linear combination? What is the definition of a spanning set? And what are the three main ways we can ask questions about spanning sets?